Very good morning. So, discrete mathematics. Today's topic under discussion, Unit 3, generating functions recurrence relation. That too will be focusing on second order linear recurrence relations, recurrence relation with constant coefficients. This will be our focus of discussion. Okay. So we are speaking about second order homogeneous recurrence relations. Let us say our recurrence relation form is this. What is this form? Cn an plus Cn minus 1 an minus 1 plus Cn minus 2 an minus 2 equal to 0 for n greater than equal to 2. This is our recurrence relation form. Here Cn minus 1, Cn minus 2, these are the constants, real constants, where Cn is not equal to 0. This type of relation is called as a second order linear homogeneous recurrence relations with constant coefficients. Why second order? We are reached from up to 2 here. And why constant coefficients? Because we have these constants Cn, Cn minus 1, Cn minus 2. We need a solution for this recurrence relation of this form. Okay. So the solution for this is an equal to c k to the power of n, where c is not equal to 0, k is not equal to 0. Now what we will be doing is we will be putting the value of an, which is equal to ckn, in 1. Once we substitute that, we will be getting this. So what we will be doing, basically an will be substituted with ckn. So this will become cn ckn plus Cn minus 1 akn minus 1 including Cn minus 2 ckn minus 2 equal to 0. Now this is a second order recurrence relation. So what we will be doing is the value of n will be putting as 2. When you put the value of n as 2, this becomes Cn ck square plus Cn minus 1 ck2 minus 1, which is 1, Cn minus 2 ck2 minus 2, which is 0. So the new equation becomes Cn ck square plus Cn minus 1 ck plus Cn minus 2 c, as k to the power of 0 is 1. Here c is a constant, so we can remove this c constant. So what our new equation becomes Cn k square plus Cn minus 1 k plus Cn minus 2 equal to 0. This is our solution. An is equal to ckn, which we replaced in our recurrence relation form. This will be a solution if k satisfies this quadratic equation. Then this quadratic equation is called as an auxiliary equation of the characteristic equation for the relation 1. For this there will be 3 cases. For the solution there will be 3 cases. Case number 1, the two roots, this is our form, right? From this we need to find the roots. There will be 2 roots, right? k1 and k2. In case 1, if the 2 roots are real and distinct, then the solution will be an equal to a k1n plus b k2n. Here a and b are arbitrary real constants as the general solution of the relation 1. Case 2 will be the 2 roots k1 and k2 are real and equal with k as the common value. Then we take an equal to a plus bn k to the power of n, where a and b are arbitrary real constants as the general solution of the relation. There will be a third case also. In the third case, the two roots k1 and k2 are complex then k1 and k2 are complex conjugates of each other. So that k1 will be equal to p plus iq, k2 equal to p minus iq, and an will be equal to r to the power of n, a cos n theta plus b cos n theta. Here a and b are arbitrary complex constants. R will be equal to mod of k1 mod of k2, which equal to root of p square plus q square, and theta will be equal to tan inverse of q by p. So let us look at few examples. Remember what we have discussed till now. We are speaking about second order linear homogeneous recurrence relation. We are speaking about this form of the equation. What is the form of this equation? Cn an plus Cn minus 1 an minus 1 plus Cn minus 2 an minus 2 equal to 0 for n greater than equal to 2. Cn minus 1, Cn minus 2 are constants. Okay. Cn is not equal to 0. What is the solution? Solution is an equal to ckn. It means what? We will be substituting an equal to ckn here. Wherever an is there, you will be putting ckn. So c and k both are not equal to 0. So when we substitute an equal to ckn here, what will happen? We get cn, ckn plus cn minus 1, ckn minus 1 plus cn minus 2, ckn minus 2 equal to 0. As it is second order, n value will be equal to 2. So once we substitute that, we will be getting this, and we will be ignoring the constant here c. So that our equation becomes Cn k square plus Cn minus 1 k plus Cn minus 2 equal to 0. Then there will be three cases we are taking. The roots k1, k2 are real and distinct. Then this solution, an equal to ak1n plus bk2n. And second case is the two roots are real and equal. Then in such case, an equal to a plus bn k to the power of n. The third case also we mentioned where k1, k2 are complex. Then k1 equal to p plus iq, k2 equal to p minus iq, an equal to r to the power of n, a cos n theta plus b cos n theta, r equal to root of p square plus q square, theta equal to tan inverse of q by p. So now let us try to understand the problems. Let us say you get this problem in the exam. What it is saying? There is a recurrence relation that need to be solved. Means what? We need to find the solution for the recurrence relation. The recurrence relation given in the question is an plus an minus 1 minus 6 an minus 2. Okay. And what is given? A0 equal to minus 1, a1 equal to 8. These values are given. Now our form of recurrence relation is Cn an plus Cn minus 1 an minus 1 plus Cn minus 2 an minus 2 equal to 0 for n greater than equal to 0. Here Cn, Cn minus 1, Cn minus 2 are real constants with Cn not equal to 0. Now from this equation what we get? The coefficients. What will be your coefficient? Cn will be 1, Cn minus 1 will be 1, Cn minus 2 will be minus 6. This. Okay. Cn will be 1, Cn minus 1 will be 1, and Cn minus 2 will be minus 6. Now what we have to do now? We have to do the substitution. How? An equal to ckn. So when we substitute an equal to ckn, what will be getting? Ck to the power of n plus ck to the power of n minus 1 minus 6 ck n to the power of n minus 2 equal to 0. Now as it is second order, the value of n will be 2. So that value of n2 will be substituted here in this equation. So when we substitute that, what will be getting? Ck square plus ck minus 6k to the power of 0, which will be equal to ck square plus ck minus 6 will be equal to 0. We are ignoring the constant, so k square plus k minus 6. This is our equation. Now this equation is called as the auxiliary equation. Now this is our equation, k square plus k minus 6. We need to find the roots, so we are rearranging this. So we are writing this k square plus k minus 6 equal to 0 as k square plus 3k minus 2k minus 6, because 3k minus 2k will be k only, right? So this, here I will be taking k as a common, so k plus 3 minus 2 as a common, so k plus 3, so k common came as k plus 3, the other one is k minus 2. So what will be our roots now? The two roots k1 will be equal to minus 3 and k2 will be equal to 2. So k1 is minus 3 and k2 is 2. So you can see that they are different, so they are real and distinct. If they are real and distinct, what we have to do? We have to take the first case. What is our first case? If the two roots are real and distinct, see here, k1, what is the value of k1? Minus 3. What is the value of k2? 2. They are real and distinct. So what is the solution? an will be equal to a k1 to the power of n plus b k2 to the power of n. So here an will be equal to a k1 to the power of n plus b k2 to the power of n. So here value of value of k1 is minus 3 and value of k2 is 2. So a into minus 3 to the power of n plus b into 2 to the power of n. Here a and b are the arbitrary constants. Now we have two cases. In the question itself, what is given? In the question itself, we are given that a0 equal to minus 1, a1 equal to 8. So a0 equal to minus 1, a1 equal to 8. So a0 is n equal to 0 equal to minus 1, a1 is 8, n equal to 1. So how we are getting this now? What is your solution has come this? This is our equation now. So an, so that will be a0 now. a0 will be equal to minus 1 and a1 equal to 8, that you have to remember. So a0 will be getting how? A into minus 3 to the power of 0 plus b into 2 to the power of 0, because n value being given as 0. So a0 equal to, this will become 1, so a plus b. a0 will be equal to a plus b. a1 will be equal to how much? A into minus 3 to the power of 1 plus b into 2 to the power of 1. So a1 will be equal to minus 3a plus 2b when n equal to 1. So now this is our equation, a0 equal to a plus b. So a0 value is minus 1, so minus 1 is equal to a plus b. a1 is minus 3a plus 2b. So a1 value is 8, so 8 equal to minus 3a plus 2b. If we solve this, how we solve this? Maybe in this form, like this, a plus b equal to minus 1 multiply by 2, so that becomes 2a plus 2b equal to minus 2. Take these two equations and you will be coming out with the value of a as minus 2 and the value of b as 1. Okay. So we get the value of a as minus 2 and get the value of b as 1. So we will be giving the solution for this, for what? An equal to a to the power of minus 3n plus b into 2 to the power of n at the end. So an will be equal to a into minus 3 to the power of n plus b into 2 to the power of n, which is equal to minus 2, because value of a is minus 2 and value of b is 1. So this will be our new equation. So we will take one more example here. What is the question? We need to find the solution for recurrence relation. This is of what order? The order is 2. So this is second order. Okay. So an will be equal to 3an minus 1 minus 2an minus 2. And the value of a1 and a2 are given in the question as 5 and 3. So this is our equation. So what we'll do is, we'll be taking this on the left side. So an minus 3an minus 1 plus 2an minus 2 equal to 0 for n greater than or equal to 2. So this is of the form second order, cn an plus cn minus 1 an minus 1 plus cn minus 2 an minus 2 equal to 0. Now what are the coefficients? Okay, our coefficients will be how much? The coefficient cn will be equal to 1, cn minus 1 will be equal to minus 3, cn minus 2 will be equal to 2. We have to refer this. Take the constant values. First constant is 1, second constant is minus 3, third constant is 2. So same thing we have put here. So how we are going to get the solution? We are going to get the solution by this replacement. What is the replacement? An equal to ck to the power of n. So this is our equation. In this equation, what substitution will be doing? Instead of a n, we'll be writing ck to the power of n. So ck to the power of n minus 3 ck to the power of n minus 1 plus 2 ck to the power of n minus 2 equal to 0. So what we'll be doing is, we'll be substituting the value of n equal to 2 because it is a second order relation, recurrence relation. So wherever n is there, you put 2. So ck square minus 3ck plus 2c will be getting. So this becomes ck square minus 3ck plus 2. So this becomes k square minus 3k plus 2. This is our equation. Okay. Now once we get this k square minus 3k plus 2 equal to 0, what will be finding? We will be rearranging them. So I am rearranging them as k square minus 2k minus k plus 2 equal to 0. So take k as common here, k minus 2, then minus 1 as common here. So we will get k minus 1, k minus 2 equal to 0. So the two roots k1 and k2 will be equal to how much? K1 will be equal to 2 and k2 will be equal to 1. So as you can see, k1 and k2 are distinct. So our solution will be a n equal to ak1 to the power of n plus bk2 to the power of n. So now a n will be equal to this a 2 to the power of n plus b 1 to the power of n. So what is given in the question? In the question, a1 value is given as 5 and a2 value is given as 3 for n equal to 1 and n equal to 2. So there are two cases here. So when there are two cases, n equal to 1 and n equal to 2, so a n will be equal to this, a1 will be equal to a2 plus b, a2 will be equal to 4a plus b. If we solve this, we will be getting the value of a as minus 1 and value of b as 7. Okay, like this you may solve this like this. a1 equal to 2a plus b, okay, a2 equal to 4a plus b. So value of a1 is 5, value of a2 is 3, and do some substitution, get the value of a as minus 1, b as 7. This you will be putting in the equation. Okay, so we will be getting the solution as a n equal to minus 2 to the power of n plus 7 to the power of n. Let us take one more example. Here equation is given as a n minus 6 a n minus 1 plus 9 a n minus 2 equal to 0, and the value of a0 is given as 5, a1 is given as 12. So same thing, this is cn value will be 1, cn minus 1 value will be minus 6, cn minus 2 value will be 9. Solution will be given by substituting this, an will be substituted with ckn. So that becomes ckn minus 6 ckn minus 1 plus 9 ckn minus 2. As it is second order, the value of n will be 2, substitute the value of n as 2. So we will be getting here as k square minus 6k plus 9 equal to 0. So k square minus 6k plus 9 equal to 0 can be rewritten like this, k square minus 3k minus 6k plus 9. So we will be getting the value of k1 as 3 and the value of k2 as 3. So what is happening here? The two roots k1 and k2 are equal. So then we have to go for the second case. Let us look at the second case now. What is the second case? Let us look at the second case. Case 2 is what? K1 and K2 are equal. If K1 and K2 are equal, the solution will be a n equal to a plus b n multiplied by k to the power of n. So let us go back there. So here K1 and K2 are both 3, both equal. So this is our solution. So here value of a0 is 5 for n equal to 0, a1 is 12 for n equal to 1. So a0 calculate it by substitution. You will be getting the value of a as 5. Then here you will be getting the value of b as minus 1. Put this in the equation and you will be getting the solution as a n equal to 5 minus n multiplied by 3 to the power of n. We will take one more last example and then we will stop. This is for case 3 actually. What is case 3? You already seen that. K1 and K2 are complex. If they are complex, K1 will be equal to P plus IQ, K2 will be equal to P minus IQ. An will be equal to R to the power of n, A cos n theta plus B cos n theta. r equal to square root of p square plus q square and theta equal to tan inverse of p cube slash p. This is the equation given. Okay, an equal to 2 in the bracket an minus 1 minus an minus 2 for n greater than or equal to 2. The value of a0 in the question itself is given as 1 and a1 is given as 2. So we'll be just shifting this to the left. If I shift to the left, this it becomes this equation, and here the value of Cn will be 1, Cn minus 1 will be minus 2, and Cn yes, it is minus 2, and Cn minus 2 will be 2. Now substitution, how we are going to substitute? An will be substituted with Ckn. So if I substitute with Ckn, and after that if I substitute n value equal to 2, our equation becomes k square minus 2k plus 2 equal to 0. This will be in the converted into form minus b plus or minus square root of b square minus 4ac upon 2a. So here we will be getting this complex roots as 1 plus or minus I. As the roots are complex plus or minus I, an will be equal to this. Okay, here a and b are constants. So r will be equal to square root of p square plus q square. P is 1, q is 1. So square root of 2. Theta equal to tan inverse of q upon p. Tan inverse of 1 by 1. Tan theta equal to 1 by 1. 1. Theta equal to pi by 4. So tan pi by 4 equal to 1. So we'll be substituting this in the general form of the solution. This is the general form of the solution, and we'll be getting this answer. Using this, now what we are doing is, as in the question itself it is given a0 equal to 1 and a1 equal to 2, we will be finding value of a as 1 and value of b as 1. This will be putting in the final solution and getting the solution as an equal to square root of to the power of n 1 into cos n pi by 4 plus 1 into sin n pi by 4. So thank you.